crash course for CFD, ANSYS approach. Today we will be talking about unsteady and turbulent flows, how we can model time-dependent transient flow fields, and especially the turbulent ones. Let's have a recall about the unsteady simulation that we talked last time. For the transient formulation, we will be having a specific function that changes with time, so we'll be having a differentiation with respect to t, and as always we would like to discretize this differentiation or this derivative, and we touched a little bit upon the explicit and the implicit formulation for the time integration schemes. And we explain the difference between the explicit and implicit ones, what are the pros and the cons of each integration scheme, or they call it temporal integration scheme. And I would like to stress again about the importance of the current Friedrichs-Lewis number, the CFL number. Last time we discussed the physics behind it. In our numerical simulation, what we are trying to do is that we are trying to capture what's happening in the real life or in physics. So if we have a wave that is traveling in the physical domain, for example, with a speed of 1 meter per second, and we are having a mesh size to visualize this physical wave speed or what's happening in nature, we should make sure that the speed of the traveling information in our numerical simulation is kind of equal at least or even slower than the speed of the traveling information in physical life. Why is that? Because we want to make sure that the speed of the traveling wave in physical life is being captured by that traveling wave in the numerical simulation. So it's more preferred actually to have a CFL number that's less than 1, because if your CFL number is larger than 1, you are not capturing what's happening in real life or in physics, and your numerical domain or numerical simulation is messing or leaving behind some information that are not being captured. Aside from reaching an unphysical or an unreliable solution, you might get some stability issues, especially with the discretization schemes for the temporal and the explicit and implicit temporal discretization schemes or time integration schemes. The pseudo-transient, when we talked about it a little bit last time, we said that Fluent was trying to come up or solve the consideration or the restrictions over the CFL that forces you to select specific delta t's, which could be a very small delta t, and you might have not this luxury to stay about for a month or a week or even a year doing your CFD simulation. So they introduced something called the pseudo-transient, where it's a fictitious time again. This is the governing equation or the conservative equation. This is the real time domain partial by partial t. However, they introduced a new time domain which is partial by partial tau, and at each time step they are solving another time domain. So you kind of having a cascaded time domains, as if they are two for loops inside each other. And once this time domain reaches steady state, which is the tau, then you can go ahead and switch to your large time domain and then go to another physical time step. This allows you to have larger time steps in the physical domain and makes sure that this system of equation, after being discretized and transformed to an algebraic system of equations, it's not going to be a very stiff system of equation, and excuse me, and inverting it or finding a solution will be a much easier task. So last time I didn't touch upon the calculation setup in Fluent. So this is the calculation setup in Fluent when we are solving transient simulation. You get to choose your time stepping method. You can have it as a fixed time step where you specify your delta t. It could be fixed periodic. And what do we mean by fixed periodic? it works with the periodic or the cyclic boundary condition that we introduced last time, if you recall. And most of the time, it's very beneficial when you are solving a turbomachinery problem or a helicopter blade, anything that is in a periodic motion. The fixed periodic time step works with that very efficiently. And instead of defining a time step, you specify the period of your motion and then the number of the discretized, or the number of points that you would like to have in your period. It's another way of defining your time step, but just kind of a convenience thing. The third approach is the adaptive time step, where your solver, the Fluent solver, gets to select the time step based on the different scales and different velocity at each point in your mesh, and it's closely tied to the CFL based. In the CFL based, you don't specify even a time step, you just specify a value for the CFL number that you would like to run your simulation at, and then Fluent makes sure that the time step is selected based on the value of the CFL that is prescribed. By this, Fluent check the value of the CFL at each cell, at each time step, because the CFL value changes from each cell to another. In one of the cells, you might have very fast velocity, but in another cell, you might have another small velocity. You could have a very fast velocity, but that cell is large, delta X is large. So at each cell, there is a value for the CFL. The second thing is that you specify the number of time steps, okay? And I've been talking about the time stepping method, but before specifying the number of time steps, let's consider that we are gonna do a simulation with the fixed time step. So how we select the value of the time step? So for the grid or for the mesh, we said we start with a very coarse one, and then we keep refine our mesh till we reach a grid independent solution. So we have a way of defining the grid elements over any mesh or over any fluid domain. But what about the time step? This is a very important discussion. For the time step, I would like to select, or that's what I do on a personal basis, based on my experience, is that if your body is not in motion, you are not solving a dynamic problem, a moving airfoil or a rotating body or anything. It's just a fixed body in the Eulerian frame of reference, and the wind is blowing over that body. What I like to do is that I check what's the period or the time constant for that flow. In other words, we check the characteristic length of our body, which usually will be 1 in the numerical domain, and then we divide it by the speed of the coming flow. When we do that, we will find the time needed for that body as if it were to move one characteristic length. So for example, if we have a free stream of 5 meters and the characteristic length is just 1 meter, this means that our body needs to move, or our body needs to take 0.2 seconds just to move 1 meter based on that speed, okay? So when we get that time constant or that time period, most probably, or the best practice is that you get to divide this period or this time constant over 550 or 200. So the one period or the value or the time constant for your shape to move one characteristic length, it's a good practice to divide it by 50 or 200 time steps, okay? So in other words, you would say, I will be simulating how many characteristic lengths my body were to move in that liquid. So if, for example, the same example, if we have characteristic length of 1 meter and u is equal to 5 meters, this means that one time constant or one period is equal to 0.2 for that cylinder or that shape to move one characteristic length in that fluid domain. And I would like to simulate at least 10 cycles for a transient simulation to get a steady state solution, or for your solution to forget the memory effects of your initialization and the boundary conditions that you're applying. So for after 10 cycles, you will find that always this number will be relevant. So it's not a big deal how much it's gonna be your delta t. If it's too small, don't be scared, because we don't mind if it's too small. At the end of the day, we want to solve 10 cycles or 30 cycles, and we are dividing each cycle by 50 to 200. So I don't mind how much is going to be your delta t, but I know to solve 10 cycles, if I'm discretizing by 50 points, I need 500 iterations. If I'm discretizing by 200 points, I need 2000 iterations. And I don't mind what's going to be the time step. If your Reynolds number is very high, which means that the velocity is very high, you will find that your time step is very small, but at the end of the day, it's not a big deal, because you are having only 500 iteration or 200 or 2000 based on that selection. So it's a nice way to select the time step. And after you do all of that, at least make sure, if you're not going to use the CFL based, that your CFL is less than 1 in most of your domain. Okay, so the question comes on how I'm going to compute the CFL for each cell. You don't do that, but at least approximate the velocity in your domain. Maybe in the far stream, take it as just U infinity. Near the body, it's best practice to have it around 0.5, sometimes 1.2, based on the physics of your body. Because if you are simulating an airfoil, the lower surface, the flow decelerates, but the upper surface, the flow accelerates. So you need to have an estimate or a quantitative value about the different velocity, and then you know the mesh size at each domain or at each place in your grid, and you know the delta t that you selected before. Make sure that at least the CFL is around 1 or less than 1 in this simulation before you are gonna do it. And the number of time steps, I explained it a little bit a while ago when we talk about this number of the value of discretizing, or it shouldn't be discretizing. It should be stepping. I don't know, for time step what should we say? Stepping, Professor? I think it should be stepping. Discretizing as well? Yeah. Okay. And one final thing in the solution controls is the iterations per time step. Remember, for the pseudo transient, we are solving as if it's a two nested for loops, one for the physical time domain and one for the fictitious numerical time domain that we are trying to relax the numerical problem with it. This second loop or this inner loop needs a number of iterations regardless of your time step. And these are the recommendations by Fluent and most of the scholars in the CFD community. If you are using the coupled scheme, and now we are expert, we know what's the coupled scheme, we need only 10 to 15 iterations. But if you're using the simple scheme, most of the time you will need around 20 to 25 iterations. I would like to hint about something that I have been noticing a while, all of the time in performing CFD simulations. Remember the residuals last time, and I asked or I told you that please do not rely on residuals for judging conversions, because they don't give you a really scientific way of what's happening. It's just give you an estimate that you are converging, you are reaching a solution, but this should not be your convergence criteria. I have seen most of the time that students does not specify this number to be around 10 or 15. What they do is that they specify this number to be around 200 or 300. And they wait. They specify a residual value, and they wait till the residuals goes down and reach around 10 to the power negative 6 or 10 to the power negative 12. at each time step, and then when Fluent detect that convergence is reached based on that criteria, Fluent automatically switched and goes to another time step. This means that at each time step you could be almost doing around 10 times number of iterations more than what's being feasible. I would like to say that this extra number of iterations does not give you any better solution, because you are already having your physical time domain, which is delta t. In the steady solutions, we specify a huge number of iterations because we want that steady state solution to reach a converged solution and does not change anymore. However, for the unsteady CFD simulation, you start with an initial condition, you have your delta t and make sure that CFL is okay, and you don't worry about the converged solution at each time step, because you are monitoring your conversions based on time history for the CL value, time history for a drag or any integral value. And you will always find that the first 5 or 10 cycles, either you are moving in a rectilinear motion, which is a steady or static shape, or you are making any rotation or any periodic motion, you will always find that the first 5 or 10 cycles has a transient component or a transient mean, but after that you will reach a steady state value or a steady state mean, but you will be keeping your dynamics or your transient values while you are going. Okay, so this is a very important step, because this will be translated to computational time. If that simulation that you're trying to solve would take you an hour to solve it, but you have 100 or 150 number of iterations instead of 10 to 15, it will take you 10 hours instead. Okay. Now let's stop talking about unsteady simulations and let's talk about turbulence. This is, I could consider it one of the most important workshops in the crash course. I'm not bragging, I'm just saying that because this workshop or this topic has a lot of terminologies, and unfortunately it was built based on experience and scholar attempts to solve the turbulence problem, which is considered as one of the most, or still the most important classical unsolved physical problem, as Richard Feynman said. So there are a lot of empirical efforts that has been done, and when computations became very good, some numerical efforts has been done, some analytical efforts are being done. You put all of this in one tank and come up with a very good recipe, you will get something called turbulence modeling. If we don't have a good sense, or at least the terminologies of what has been happening, it might be very difficult to understand what turbulence model that is convenient for your problem, which one do I select, what are the limitations and the power of each one. So I think this might be very useful for anyone who's trying to do a CFD simulation, and it will clarify a lot of unanswered questions. Okay, so what's turbulence? That's an easy question. This is a turbulent flow, this is a laminar flow. If you have a laminar flow, everything is laminated above each other. Each sheet respects the one that's above it, and there is no momentum exchange between these layers. But for a turbulent flow, it's a chaos. Everything goes everywhere, fluid particles are moving, there is a momentum exchange between each layer and the other layer, and that nice quiet flow that we know is no longer governed by the simple diffusive term in the Navier-Stokes equation, because you have momentum transport, you have velocity field coming normal to the mean stream, and everything is changing. And this mainly relies for turbulent flows. When the Reynolds number increases, the turbulence becomes more and more and more. Most of the time, turbulence are classified as an unsteady three-dimensional phenomena. that's what is most of the time written in textbook. Why is that? Because of something called vortex stretching. When you have a vortex and you would like it to stretch, it cannot stretch in a 2D domain. It must stretch or convect or warp in a 3D domain. And there are different scales. When you watch a turbulent flow, you most of the time see very large vortices or very large eddies, but at the same time you will see very tiny scales and very small eddies. Something like that. You will be able to see here like one of the large eddies. However, inside the flow here there are small eddies, and as you keep going, those large scales are being discretized or are being break down by the turbulence phenomena till you reach very small scales of turbulence. And that brings us to the very good question: what are the size of the large eddy scales? Most of the time, the size of the large eddy scales are compared to the body. If you have an external flow, your large turbulent scales are of order of length of your body. And for a free shear flow, at this example, this is a jet that is being impinging in an open atmosphere. You will see that these sizes of the large scales are of order of the length scale of that diameter of that jet. So most of the time, the large scales are of order of your body, of the body or the flow field. And this brings us to another question, which is called the energy cascade. What's the energy cascade? The energy cascade is a way that happens, or it's a physical or natural phenomena that naturally emerges in turbulence. What happens in the previous picture that I was showing is that those large scales, they kind of inject energy to the smaller scales. So the smaller scales starts to create, and they kind of attract the energy from the large scales. That's why the large scales break down and they transform to those smaller scales. And those large scales, they transfer the energy to the smaller scales, and this energy cascade thing, or this energy transfer, keeps going and going and going, which means that when you have smaller scales and smaller scales, you are injecting kinetic energy in those smaller scales till they diffuse. What diffuses, or till they dissipate? What dissipates the all of that kinetic energy is just the thermal energy at the very tiny scales. But the question lies now, what is the smallest tiny scale? Which are these scales where energy dissipates? What are these scales? Because if you would like to do a simulation and you would like to resolve turbulence, your mesh or your grid sides must be smaller than those scales so you can capture them. This question was answered by Kolmogorov, where the smallest or the tiniest scales are called Kolmogorov length scales, and these small length scales are denoted as eta in the literature. And another quite interesting thing about turbulence is that regardless of the nature of your flow, if it's a flow around a free shear layer, or flow around a body like a boundary layer flow, regardless of that, if you have turbulence, nature will always adopt this slope of the energy cascade or the energy transformation that transform from large scale to small scale to be always -5/3, which is something phenomenal. In other words, if you brought a probe in your experiment and you recorded that velocity and then computed the kinetic energy and thus found the power spectrum density, this is the spectrum density, but I don't want to be very detailed and scientific, I don't want to be boring, you will find always that this, and plot this spectrum analysis, you will find always that this slope for that line is equal to -5/3. And this is a very important thing. Why is that? Because if you are doing a turbulent simulation and you would like to judge your accuracy of the flow field, as we said before, like the y plus or another variables or the mass imbalance between the input and the output, you can have a probe, a single probe at a random location in your flow field, store excuse me, store the velocity, do that power spectrum analysis, plot it. Your simulation, if it's correct and the turbulence are simulated in a natural way, the slope of that line must be equal to -5/3. Okay, and that eta, which is the smallest scale, it's called the Kolmogorov length scale, is equal to your Reynolds number to the power -3/4 multiplied by L, where L is your characteristic length. Now let's have an example and try to calculate what is that eta. So for a Reynolds number equal to 10 to the power 5. Okay, by the way, this is not a huge Reynolds number. Airplanes fly around 10 to the power 7, I think, and if it's very big, I don't know if someone reached 10 to the power 9, but I think it's 10 to the power 7. But just for Reynolds number 10 to the power 5, this is considered as kind of a low Reynolds number in aerodynamics, especially in aerodynamics. If you computed eta, which is the smallest length scale, that your grid size should be kind of at least 4 or 5 or 6 times smaller than that to capture those eddies, that eta is equal to 1.7 times 10 to the power -4. So good luck of having a grid size, and it's not, you shouldn't have that small grid size near the boundary or when you have a shock wave, as we have been talking. No, your whole domain must be kind of in that sense, because you don't know how turbulence is going to move or emerge. Okay, and this gives us a sense that this type of performing the simulation to resolve the Kolmogorov length scale is very hard, and it has a specific name. I will introduce it in a couple of minutes, but just keep that in mind. Let's consider the types of turbulent flows. I have been mentioning them, but let's explicit clearly. We have free shear turbulent flows, where you have a flow, a jet that is being discharged in an ambient atmosphere, or you have the wake of a cylinder, not the flow over the cylinder, because the flow over the cylinder is not considered as a free shear flow. You could have a mixing layer where you have a velocity here around like U infinity, but this flow is stagnant, and when these two liquids or these two fluid layers come in contact with each other, they start to develop turbulent scales. The second type of the turbulent flows are called boundary layers near solid walls, or boundary layer flows. They are always available or can be seen in outer flows if you are simulating a flow around the cylinder, an airfoil, an airplane, whatever. Why is that? Because you have here on that wall the no slip boundary condition, and you are satisfying that no slip boundary condition, and up there you have your U infinity. Nature cannot satisfy 0 and the maximum value at one point. You will get discontinuity. That's not physical. So what nature does is that it tries to smooth your velocity profile from a 0 value on the wall up to the maximum value that it can reach up there, and it gets a kind of a smooth shape. But you can see that this transitioning between a 0 value and a U infinity, it kind of possesses an exponential behavior. It happens very fast with a very steep gradient near the wall, but the gradient becomes very lower and lower as you reach the free stream or the maximum velocity. And another thing that we would like to consider is that and because of that steep gradient, if you are trying to have a grid or a mesh to solve this problem, you will always find that, or you most of the time must need something called boundary layer treatment or boundary layer mesh, sometimes called inflation in measures or CFD codes. And as you can see, these number of elements their dispersion or their size change in the same behavior that are near to the velocity profile that you will capture. For the steep gradients, you need very small elements to occur so you can capture that shape. And as you go above and above where the steep gradients doesn't take place anymore, you don't need that. It behaves in the same manner in every bounded flow in nature. So no matter what you're trying to solve, airfoil, airplane, cylinder, a car, whatever, I don't care. If you zoom too much till you are near that wall, you will always find that this velocity profile has a universal trend. This is something built in nature, something like pi. If you always draw a circle, that ratio between the pi and the diameter, that ratio between the circumference and the diameter will always pi. Why is that? Nature is built like this. So this curve or this graph is a built-in property in nature. But what's that curve? It's called it relates a couple of things inside the boundary layer. First of all, they compute something called the shear velocity or the shear stress velocity, which is at the wall. You get your shear stress at the wall divided by the density, you get u tau, okay? And then you find your velocity, your u infinity or your maximum velocity divided by u tau, you get now a non-dimensional velocity. It's noted as u plus. It turned out that this u plus, which is the y-axis, could be approximated to be as if it is a function of this whole non-dimensional value. And this non-dimensional value, which is the x-axis, it's called the y plus. And you will find that y plus is defined as this. It's rho density multiplied by u tau multiplied by y over eta, which is actually the Reynolds number, but instead of your characteristic length, you are considering your y, which is the height inside the boundary layer, and you are considering the viscous velocity or the shear stress velocity. Now, if we perform a lot of experiments, we will find that the relation between this y plus and this u plus is always like that. And it could be divided into different regions. What are these regions? The outer region, which is kind of from that blue line up to that blue line. All of this region in your y is the outer region, and from the and actually the y region and the log region. So this could be considered as the outer region and the log region. And from that blue line up to that red line, it could be considered as the buffer region. And from the buffer region, and after the buffer region, from that line or that height till you reach the wall, it's called the viscous sublayer. Why are they mentioned like that? Because in the viscous sublayer, most of the time, viscosity dominates everything in what's happening there inside the boundary layer. Momentum doesn't get to play a very good role, so that's why it's called viscous sublayer. When you go away a little bit from the surface of the plate or the shape that you're trying to solve, you get the buffer zone. They call it the buffer zone. Why is that? Because as you can see, in that viscous sublayer, y plus is actually equal to u plus. It's a curve. It's a curve because this is a log it's actually a semi-log. It's not a log. If it was a log, then it must be a straight line. This is a semi-log, so the x-axis is taken to be log, but the y-axis is not. So if y plus is equal to u plus in this viscous sublayer, you get that curve. And then you get a relation between the y plus and the u plus, which has that relation, the log relation or the natural logarithmic relation of that straight line. This relation defines the mixing that's happening inside the fully turbulent log low zone and the kind of a little bit of the outer region. Okay, this log law is verified experimentally, and this behavior as well is verified experimentally. So why I'm trying to say that, or I'm emphasizing this too much, because if we are having a turbulent CFD simulation and we are solving that flow field, regardless of the way that we are trying to resolve the turbulence, our solution, our CFD code, must satisfy this y plus, because this is pi. You cannot draw a circle without satisfying pi. I don't care how you are drawing it. You can draw it with a protractor, I think so. You can draw it with a piece of a rope. You can do whatever you like. What's the way of your implementation? But at the end of the day, pi must be reserved or reconstructed. So we can resolve turbulence however we would like to do, but that curve or our flow velocity inside the boundary layer must satisfy that. So you are more than welcomed to pick a point in your flow and try to plot this curve for your simulation. That would be a very good, nice exercise. But however, this is not the norm in verifying the turbulence convergence of your code. What is the norm? The norm is that, as you see here, the y plus values, when u plus is equal to 0, it's equal to 1. Okay, and it could be less than 1, but usually the plot is truncated at 1. Okay, why is that? Because if this is a log scale, so if u plus is equal to 0 and u plus is equal to y plus at this point, and we are taking the log, so anything to the power 0 must be equal to 1. So that's why you will find that y plus values at the wall should be at least 1 or smaller. So if you are trying to do a CFD simulation, you are urged to actually plot the y plus value at each cell over your shape or over your body. And all these values for the different cells must be lower than 1. If they are higher than 1, then you are not resolving in your simulation the viscous sublayer. You are starting, for example, your simulation from here, from 5. If you found that your y plus value is around 5, this means that your CFD code or the CFD simulation is only resolving up to here. What's happening from here to there are not being captured in that simulation, which is actually could be a big major difference, because what drives the whole simulation is the boundary condition, and what's happening near the wall is the boundary condition. Okay, so enough about the y plus, and let's talk about capturing all turbulent scales. I mentioned a while that to capture all turbulent scales, the grid size must be smaller than the smallest scale. For example, if I have that scale and this is my grid size, then I'm not capturing that eddy. I don't know what's happening inside. I need to discretize more. And to keep doing that, if we were to do this, if we got our Navier-Stokes equation and then did our spatial and temporal discretization to the Kolmogorov scales till we reach that eta scale. Do you remember that eta scale? I'm gonna generate a mesh, that's fine. If we are gonna be doing so, then the type of simulation that we are performing is called direct numerical simulation. It's a brute force numerical simulation, and it's called DNS. It seems plausible to do something like that. We can do it. This is the most not the most practical, but the most correct way. There is no approximation. There is nothing. I have that PDE. This is the physical phenomena. I would like to capture this physical phenomena. Go and discretize it. But actually, good luck doing this DNS simulations, because they are quite expensive. And I did this example to give you the sense of what do I mean by expensive here. Expensive, I mean that the humanity was not able to solve something more than 5,200. That was in a published paper in 2013. Maybe they reached now, but that paper was bragging that they were trying to reach the maximum Reynolds number. And by the way, this is only in a channel flow, DNS over a channel flow, like you have a pipe with a Reynolds number of 5,200, and you're trying to solve a DNS simulation. And to do that, they had a 242 billion elements. Their mesh is composed of a 242 billion elements, okay? And they needed a 786,000 cores. In other words, if you have your i7 processor, it's composed of 7 cores. They needed 786,000 cores of that, and more than of 130 terabyte of RAM, not of storage, of RAM. They need the RAM to be of order of this size to invert their matrix, which is 242 billion size matrix. Okay, you do this kind of simulations on a supercomputer like IBM Blue Gene, whatever. This is quite extensive. So it's not in our lifetime to see a full DNS simulation over an aircraft, for example. I don't know if someone attempted this or no, but I don't think no one attempted. So that's why we need to model turbulence. Unfortunately, we have to come with a way to model the turbulence in our flow field. And this brings us to one of the first and the most important modeling techniques in turbulence, and it's called Reynolds average Navier-Stokes equation. Why is that? Because let's consider that we are having a turbulent flow where our velocity is fluctuating, but there is a mean over that fluctuation. Then we can do something referred as Reynolds decomposition. Consider that your velocity is equal to an average value plus a fluctuation. If we do this decomposition, plug it again in the Navier-Stokes equation, which is the equation that we are trying to solve, and respect the averaging rules, you will find that the Navier-Stokes equation, which is, this is the convective term and the unsteady term, and this is the pressure gradient, and this is the shear stress term, you will find that we will end up having extra terms in the equation, which is that term. Remember last time we used to have this as our Navier-Stokes equation, and we were happy with that. Now we have this extra term. There is a new term in the equation. We don't know anything about that term till now. We would like to understand how this term behaves. We would like to quantify it, model it, and come up with models or schemes to be able to solve it. First of all, these terms are called Reynolds stresses, based on Reynolds work, and extra terms means extra equations. Because if you are solving for U, V, P, and rho, 4 unknowns in 4 equations, now you have an extra unknown. You will need an extra equation that must be solved simultaneously with your full Navier-Stokes equation. And this is the Reynolds average Navier-Stokes. If we bring the Navier-Stokes equation, we respect the averaging or do the averaging, and then do our spatial and temporal discretization, then do the turbulence modeling, because we haven't talked yet about that term. What's going to be the equation for U prime? U prime is not something like U bar. Think of U prime as if it was another variable. I will call it, for example, Nabil. So we would like to quantify Nabil in this equation. So, okay, do not be confused by the U's here. So we would like to model it, do the turbulence modeling. Then we will get the Reynolds average Navier-Stokes equation. It's called RANS. I would like to stress a very important thing, that RANS could be done or could be implemented using any of the schemes for discretizing our PDE. If you are going to solve the Navier-Stokes equation using finite element, you can use RANS. If you are going to use the Navier-Stokes equation using finite volume, you can use RANS. So turbulence modeling, RANS and DNS and the extra terms that we're going to talk is a different animal, and it's independent from what's happening in the numerical problem or the discretization. Actually, you could do your PhD in in turbulence and come up with a new turbulent model without being an expert guy in CFD simulation, and you might not write your own CFD code. You're not a numerical person, so you're dealing with physics and equations. Okay, I would like to stress that very much, because sometimes I see people confuses the terminologies of RAND, DNS, and then we'll mention a little bit about LES, DES, other stuff with the finite volume, with the order of the scheme. What's that? Okay, so now it's a clear message. It's a clear message. This brings us to the turbulence closure problem. This system of equation has a hole in it. It must be closed. And there are a lot of attempts that closes this turbulence model. One of the most early attempts, it was by Brantel himself. Brantel is a very famous, if not the most famous guy in aerodynamics. He's considered as the godfather of aerodynamics. So he was trying to solve try to provide a closure for that Reynolds stresses, that extra term. And what he did is that he assumed that the new extra turbulent term is just equal to, or will behave as if it's exactly as the Newtonian viscosity or the regular viscosity that we have. We have a coefficient of viscosity multiplied by the velocity gradient. And he took the velocity gradient of the mean flow, because we cannot compute the velocity gradient of this term. And instead of multiplying it by the same coefficient of viscosity, the natural one, he multiplies it by something called mu turbulent, the turbulent viscosity constant. And then he quantified that turbulent viscosity to be in that order. So you can come up with a number that gives you directly what's t tau. But as you can find, there is no equation is being solved here while you are doing this CFD simulation. That's why it's called the zero equation model. It's kind of, there is no dynamics. It's an algebraic model. Give me that number, I'll give you that number. There is no dynamics, okay? The second model is called Spalart-Almaraz. It's the most famous model in aeronautics field, because it was specifically developed or designed for airfoils, for flow over airfoils. Spalart and Almaraz, both of these guys are very famous and well-established scholars. I think both of them are still living. And both of them works in Boeing. I don't know. I'm sure that Spalart works in Boeing, and they still works in Boeing?
Spalart, yes.
Spalart, yes. I don't know about Almaraz. Yeah, okay. So Spalart and Almaraz developed that one equation model, and that's how they developed their equation model, their closure model. They relied on the kinematic eddy viscosity, which is again mu tau, the kinematic eddy viscosity. But instead of multiplying it with just that gradient, they multiplied it by the strain rate tensor of the flow field. And they modeled, or they approximated, that turbulent viscosity, or that kinematic eddy viscosity, by this function, where they use this kinematic V constant. And to find that kinematic viscosity, they solve this ordinary differential equation, or actually this PDE, while you are solving your Navier-Stokes equation. So that's why it's been named as one equation model, because you are adding one PDE to your system of equations. The second model, it's called K epsilon. It was developed by Wilcox, and I think he's still living. He wrote one of the most famous books in turbulence ever. And it's called the Wilcox model, by the way, if you Googled it. This model is a two equation model. I would like to mention that there is a big leap between the one equation models and the two equation models. Why is that? Because the one equation model relies on defining the viscosity or the turbulence in terms of just a mu tau, and that mu tau is a function of your kinematic viscosity, as if they are defining another property of your liquid. That's why they have only one equation model. However, starting from the two equation models and going above, there has been a leap in the physics, or the it's the physics of understanding turbulence, where Wilcox assumed that he will use the K, which is the turbulent kinetic energy, and epsilon, which is the dissipation rate of the kinetic energy in the turbulence. And now they are trying to come up with a clever model that actually mimics the log behavior for the energy cascade that I was trying to explain at the beginning. This sets the two equation models starting from the K epsilon as if they are complete equation models. Because the Szilard-Armour's model requires a lot of experimental testing and a lot of tuning. Actually, there are a lot of constants that are defined in those turbulence models, but the sensitivity of your results based on the value of the constant that these turbulence models are tuned to are very high in the Szilard-Armour's model, but they are not that much in the two equation models going beyond, because actually most of these constants in the second equation models are being computed while you're solving your CFD problem. Okay, so that's a very important point. But the K epsilon model had some of its drawbacks. I will mention it a little bit in a while. And then came up the K omega model. And the K omega model, I think it's another model by Wilcox. And it has some its good things and bad things. And the difference between the K epsilon and the K omega is that they just relied on the specific dissipation rate, which is omega, instead of the dissipation rate itself. And by the way, the list goes on. You can come up with your own turbulence model, but good luck with doing the experimental work to validate that turbulence model and come up with the constants and that nice, well-established scientific recipe, to be honest. For references, I totally encourage these two references. This is the Turbulence Modeling for CFD, it's obvious, by Wilcox, and Turbulent Flows by Pope. These are one of the most famous books in turbulence, and I totally encourage anyone to go through these books. Now, what's the difference between K epsilon and K omega? Because you will get to choose. Now, time begins. This is the difference between them. The K epsilon behaves very good in a free stream, but the K omega does not. Why is that? Because it's very sensitive to the boundary condition. If you specify the fluctuation or the turbulent fluctuation of your turbulence constant of the boundary condition, the K omega is very sensitive to that. You might find yourself finding larger drag or lower lift based on the boundary condition that you are applying, and turbulent or fluctuations or turbulent properties in the boundary condition must not actually change the flow field that much. And again, as I said, the K omega is very sensitive to the inlet and outlet boundary condition. K epsilon is not that sensitive. In the boundary layer, the K epsilon is acceptable, but however, K omega behaves very good inside the boundary layer. And for high pressure gradients, or in other words, if you have a very curved shape, the K epsilon has a bad behavior actually. I don't like to say that word, but it's kind of a bad behavior. But however, the K omega is very superior compared to K epsilon if you have a large curvature. And moreover, these two models, if you have a separation or a large separation in your flow field, they are not that good, both of them. And we will see in a while that actually the whole RANS field or the whole RANS way of approximating turbulence is not that good if you have severe separations or vigorous mixing and very complicated structures of your flow field. But let's say now, what should we do if we see something that's not that good? It's the main theme of the workshop. We enhance it as we did with the central differencing scheme. We came up with the upwind scheme. Okay, K epsilon is not good. Let's find the realizable or the RNG K epsilon. Most of these models overcome some of the drawbacks of the K epsilon and K omega, but I don't want to waste your time more on that. You can just Google K epsilon realizable versus RNG. You'll find tons of actually forums and talks about it. And for the K omega, we would like to make another extension, and the extension for the K omega is called SST. This is one of the most famous turbulence model now, if not the most famous. It was developed by Mentor, and it's called the Mentor model. And by the way, I would like to say something, that the K omega SST is not more than a blending switch. It takes the good from here and the good from there and blend it through a switch. It applies K omega near the boundary layer when it has a superior performance, and then when you go far from the flow field, it applies the K epsilon. However, it's the most famous turbulence model, but I would like to mention again that both models, the K epsilon and the K omega, the original ones, were developed by Wilcox, but that blend is developed by Mentor, and Mentor is now the scientific chief, I think, of ANSYS company. Okay, so he's hired by ANSYS company as the scientific chief of the research development, something like that. And he's still living, and he's still living, and he works in turbulence still now. Now that's what you get. This was the prescription that I have been mentioning. You have inviscid laminar, but you have Spalart Armalosov. It's a turbulent flow, K epsilon, K omega. Now, two equation models are not that good. They don't behave well in the separation. What should we do? Scholars came up with another model, the transition KKL omega, 3-equation model. The transition SST, 4-equation model. The Reynolds stress, it's a 5-equation model. This is not considered as a RANS, to be honest. This is not a Reynolds average Navier-Stokes equation that much, but it could be, no, actually, sorry, the scale adaptive is not a RANS. The Reynolds stresses is still a RANS CFD simulation way. But I'm not going to talk about these equation models, to be honest. I have not used any of them, and I'm not that expert about them. We can just Google them. And I will save the time to come about talking about other types of modeling the turbulence model, which is the detached eddy simulation. And before talking about DS, I have to talk about another type of simulation, which is called LES. So let's wrap up the RANS characteristics. They are computationally cheap. They require moderate meshing plus schemes requirement. They are not that numerically, how do I, they are not that needy. They don't force you to come up with the best mesh ever, with the best scheme ever. They are nice, kind guys. They work with everything. That's why they are considered up till now as the working horse of all the engineering results in the community. So if you're going to work in a company, in an applied company, most of the time they are going to use RANS, or you're going to switch to another fancy thing that I'm going to mention in a little bit. But however, the bad thing is that they model most of the turbulence scales. So as we have seen before, we have large scales and we have smaller scales. They only resolve that scales, which are the very large scales that are compared to your body shape, characteristic lengths. But starting from here, going down to the dissipation, all of that is being modeled. It's not being resolved by the equations. And what's the drawback of that? That's what you get. If you are going to solve a DNS simulation for a jet flow, that's what you get with the DNS simulation. But if you're going to solve that simulation with the RANS, you'll get a very diffused solution of what has been happening in reality. So this means that it's not quite good. We would like to have another thing that might act a little bit better, and that brings us to, and they fails actually in massively separated flows. If you have a massive separation and vigorous interaction between different turbulent scales, they totally fail. This brings us to the second type, which is the enhancement. It's called large eddy simulation. And what's the main idea about the large eddy simulation is that they resolve large scales or large eddies instead of modeling them. What do I mean by that? Is that consider as if this is our grid, and anything that could be resolved, by this grid size, then I'm capturing it. Anything that's smaller than my grid size, I have to model it because my numerical solution doesn't see it. How this is being performed? It's being performed through a filtering equation. They filter the Navier-Stokes equation in the space domain, not in the time domain. I know it might look weird a little bit, but it's the same as the Fourier transform. If you are familiar with the Fourier transform, you can write your Fourier transform equation, but instead of having the t as the independent variable and you integrating over t, you can just integrate over x or whatever domain you can have, okay? So they spatially filter the equation, and that's the equation for the filtration, but this is in the time domain, not in the frequency domain, and this is called the convolution, but I don't want to be that technical. But the filter bandwidth, or the filter cutoff frequency, is considered as your grid size, as we have been talking from a minute. Anything that's smaller than your grid size, you're not capturing. Anything that's larger, you are capturing. So actually, the large eddy simulation makes total sense, because if you have a very, very fine grid to an extent that you are capturing all scales, you could actually consider yourself doing a DNS simulation. And there is no Lilly model. And again, what they assume is that they have the shear stress for the subgrid scales, and they assume that function for that tau term, and then they go and compute the coefficient of viscosity and the tau as a function of the, as you can see here, the filter size, which is the large delta, and couple of constants, and the strain rate. I don't want to be very technical about that, because most of the time, if you are a Fluent user, you will not code something like that, but it gives you a very good sense of what's being implemented. The Smagoritsky model faces some problems. I forgot what was the problem. It was something related to, I think, dissipation or something like that. I forgot the problem of the Smagoritsky, to be honest. So they developed the higher order model and the advanced model, and you keep going. But I actually, it flies from my mind what was the difference between these three models, to be honest. I'm sorry about that. So I might put a caption in the YouTube video, so stay tuned for this. And that's what you get. If you do an LES simulation, you get something in between the DNS and the RANS. So obviously, large eddy simulation are kind of, or considered as the second promising working horse now in industry, because computational power became very good and very reliable, and one can rely on LES directly and do not go for a RANS simulation. But the bad thing for, or the characteristics for LES, it's a 3D unsteady only. Actually, in the menu that I was showing from Fluent a couple of minutes ago, LES was not there. Why is that? Because I was just taking a screenshot from a 2D simulation, and it was a steady simulation. Even if it's a 2D simulation and you enable transient, which is an unsteady simulation, Fluent will not give you the option to select LES. Okay, so LES is considered a 3D unsteady simulation only, and they are cheaper than DNS. They can handle massive separations, and they can handle massive pressure gradients, but they are extremely expensive for boundary layer flow. If you're going to solve not a free shear layer flow, if you're going to solve a boundary layer flow, some people say that you could actually go and solve DNS. And that's why there is something called wall modeling or wall modeled LES. They do not take the LES solver as it is till you reach the no-slip boundary condition. They actually model the wall behavior inside the LES solver to relax the costly or a very expensive requirement for computational hardware to solve it. Because otherwise, you could go and solve DNS. It's not going to be the same cost, but it's very costly. And on the bad side, again, they ask for harsh mesh requirements and scheme. They don't work with any mesh like the RANS kind way of simulation faults that we have. They need very orthogonal grids. They need very specific schemes. They don't work with the upwind schemes because it includes the high dissipation and diffusion in the flow field, as we can see in the RANS. you must work with the central differencing, but we know that the central differencing is not that stable. They developed specific schemes in Fluent just to solve the LAS simulation. So it needs quite time to be able to solve an LAS simulation. And for reference, I totally encourage this book. It's a very good book as an introduction for large eddy simulations by Sagaut, and it's a Springer book. It's not a yellow book of Springer. This could be a joke. Someone could understand it. It's just an orange book. So do not confuse it with yellow Springer books, because yellow Springer books has their own type in academia or place in academia. Okay, so now let's say what we are trying, or yes. No, it could be performed for anything, compressible, anything. But this book is just for incompressible as a simple introduction for LAS. That's what I'm trying to recommend. Okay. Now let's see the story of the turbulence modeling till now. We have Reynolds average Navier-Stokes equation, which is called RANS. That's what you get by RANS. And you have large eddy simulation, and that's what you get by LES. In RANS, you do the averaging. You come up with a recipe to find the shear stress terms or the Reynolds stress terms. And the LES, you have your spatial filter and you have your subgrid scale models. The pros of this type of modeling is that they are cheap, they are doable and accurate near wall, but turbulence is modeled in all the flow field. And here, the turbulence is resolved instead of being modeled. They are doable and accurate in free shear, and they are extremely expensive near wall. Now, this gives us the idea, or it triggers the thought of, let's do the blending thing. Why don't we utilize LES where it's very good and cheap, and then utilize RANS where it's very good and cheap and it's not missing the solution? And yes, this has been done. It's called detached eddy simulation, or unsteady RANS, which is the unsteady version of the Reynolds average Navier-Stokes equation, because as I told you guys earlier, LES solver are inherently 3D and unsteady. So we need to just have the unsteady version of the Reynolds average Navier-Stokes equation, which is not a big deal. And the unsteady RANS is being developed, or is being implemented near the wall, but the LES is being implemented outside the wall or far away from the wall, where the flow could be considered as if it was a free shear flow. If we have the Navier-Stokes equation plus spatial filtering plus spatial and temporal discretization, because remember we're doing LES now. Remember here we had the subgrid scaled modeling. Now instead of just having the subgrid scaled models, we have the RANS model as well. And the whole clever idea about the DS simulation is that the RANS model, which is K epsilon or K omega or whatever, could actually be used as if it is the subgrid scaled modeling for the LES solver. So when you are solving DS simulation, you are not actually using the Smagorowski-Lely subgrid scale modeling. No, you are using one of the RANS model to act as the SGS model for your LES. This is the clever trick that allowed the detached eddy simulation. And again, by the way, the two fathers or godfathers of the DS simulation are Spallart by himself and Mentor, and there are other two guys, I forgot their names, okay? And there is a very seminal paper by Spallart and Mentor, and these other two guys that I forgot their names. No, they are living. And actually, the good thing is that they knew that this paper would be the cornerstone of a new area of simulation, to an extent that when they were listing the authors, they literally said the authors are listed in alphabetical order and the contributions are exactly the same. So anyways, so when you do that, you get the detached eddy simulation, okay? And the first detached eddy simulation, we need in the detached eddy simulation a way to set the boundary between the unsteady RANS and the LES. We need to select that. In the first one that was developed by Spallart and those other three guys, the DES, or that boundary, was induced by the mesh. So in other words, the CFD implementer should be clever enough to be able to mesh the elements and the dispersion and the rate of growth and the size of the elements in a way that to be able or to force the solver to activate the RANs in the area where RANs is more efficient, where high viscous forces are there and LES cannot penetrate in this region, and activate LES where the flow could be approximated as a free shear layer. So this was actually a very tedious thing to do. So they came up with another version of the DS simulation where it's called delayed detached eddy simulation. I don't know why the name delayed, but the delayed detached eddy simulation is not more than, it has a shielding function. What the DDES does is that it has a shielding function that prevents LES from penetrating inside the unsteady range solution, and the unsteady range solution from penetrating or extrapolating in the LES solution. Because remember, if LES goes in the unsteady range, that mesh here is not prepared for accepting an LES solver. So what you will get here will be totally non-physical. And if the unsteady range extrapolates in the LES, that mesh is acceptable to accept the unsteady range solver, but the solution you will get here will be of an unsteady range nature. You will be damping all the scales that you would like to capture as actually, and you have been doing all of that to do this. But that shielding function was not performing in a very good way, and they come up again, both of them, the three of them I think, or the four of them, came up with the final version, which is called the improved delayed detached eddy simulation, where in that improved delayed detached eddy simulation they utilize wall modeling large eddy simulation. So the boundary layer flow is not being captured by the RAND solver only. No, it's actually only the viscous sublayer. If you remember, that very small layer is only captured by the RANs, but the log layer and the outer region up to the external flow is being captured by the LES solver, and this enhances the results very much. Let's see an example here for the turbulence model and the difference. Now, I might ask questions now. On the left-hand side, what type of solver do we have? Actually, not solver, turbulence modeling. I'm sorry. What type of turbulence modeling do we have? Yes, on the left-hand side, we have RANs. On the right-hand side, it could be large eddy simulation, but actually it's not a large eddy simulation, it's a DS simulation. And you can see the differences, especially at larger angle of attacks. When you have larger separations, you have a lot of mixture here. You are having a rich dynamics that's happening over the wall because of the wall modeled large eddy simulation, but here you're not having other than a diffused vorticity contours of what the flow field could be like. And it's a big deal because there is a difference. If you compare the CL values, you will find that the maximum value here is around 2. For example, 2 or 2.1, but here the maximum value reaches to up to 2.5. So the scales or the flow features that you are capturing might actually affect, at the end of the day, the integral quantity or the whole goal behind designing this machine or whatever. This is a simulation for a pitching airfoil that could be considered as if it's for a windmill or a helicopter blade. If someone relied on unsteady RANs or just RANs, someone could say, oh, that airfoil will not give me that specific amount of lift or power that I'm trying to get from that windmill. But however, in reality, it could if just someone changed the CFD simulation. These two CFD simulations are considered correct simulations. They are converged simulations. They respect the CFL. They respect the time step. They respect the turbulence convergence, and all of the precautions and guidelines that I have been trying to mention in the last two lectures and starting from this one has been considered in the simulations. But again, just because one way of modeling the turbulence is totally different from the other, you are getting two different spectrum of the results. Okay, this doesn't mean that this is a wrong simulation or that's the wrong simulation, but anyone who is implementing a CFD simulation should again know the limitations and the power of that simulation. Okay, so that's the main message that I'm trying to invoke here through this whole workshop. The CFD simulation really is good as is the person who is implementing them. This is the same CFD simulation, but this is 3D ISO contours. And as you can see here, even if that is a 3D simulation, you're just not getting more than the edge of the vortex is being extruded in the 3D domain. However, because we are utilizing the large edge simulation here, we get those, they are called ISO contours, but we are getting those fancy contours of turbulence mixing, especially when 3D when not 3D, especially when massive separation starts to occur. You cannot get any of these solutions using a RAND solution. Okay. Again, this is a difference between the three of them. This is the unsteady RANDs, and this is the DDES. There is no wall modeling here. This is the delayed detached edge simulation, and as you can see, there is a difference between it and the improved one. The wall modeling LES gives you a better turbulent resolving scales over the turbulent boundary layer. Here, the solver is kind of trying to capture all these scales. Here, good luck with those scales. So I'm not trying to put the RANDs modeling in a bad situation, but you get what you paid for. That's it. Okay. And that's why I was trying to highly stress that doing a CFD simulation could be sometimes very expensive, because these two simulations must be done in a 3D fashion. You cannot do it in a 2D. Even if you tried, you will not get a good result. And the 2D and a 3D simulation could be considered as if 25 or 45 multiples of your 2D simulation. If you have just a planar mesh and you're gonna extrude it in the Z domain with just 25 or 40 elements in the Z domain, so your simulation now is 25 or 40 times larger than one single 2D case. And all of these simulations must be done in an unsteady fashion. So one case from the IDDS simulation took me on an Intel Xenon processor with 6 physical cores, not hyper-threading, around 3.5 days or 4 days, just one simulation for 15 cycles. Okay, I can do, or anyone can do, that simulation on the HPC, actually not utilizing the full capacity and power of the HPC, and I'm trying to solve this now, just in around 12 hours or 10 hours. And if you are trying to do multiple simulations at the same time, I used to send to the HPC 10 cases at the same time. And each case has around 48 cores. So we are speaking of as if I had a computer under my own disposal with 500 cores. So that's why I'm I'm trying to emphasize. Thank you for that. To emphasize that using Fluent on HPC is a very big deal. Now, performing turbulent simulation, we need the summary and the last minute slide. First of all, classify your problem. Is it a free shear layer or a severe or a boundary layer problem? Because there are two different spectrums. In one of them, you are satisfying the no-slip boundary condition, where boundary layer must be resolved, log layer, Y+, severe shear stresses, etc. In the other one, it's much more easier, and all of these restrictions are not invoked over your simulation. And the complexity, do you have severe pressure gradient of your shape? Do you have severe separations? Like, for example, the unsteady RAND simulation cannot predict even a static CL coefficient for an airfoil beyond stall. The static CL coefficient around after 15 degrees angle of attack. If you have beyond stall and massive stall, the Reynolds average Navier-Stokes equation does not give you even comparable results with the experiment. The difference is huge. Okay, so that's what one of the drawbacks of the RANS model. The second step is select your modeling technique based on what you have. You acquire the physical sense of your problem. Select the modeling technique, either RANS, LES, or DS, whatever you are interested in, and then do the meshing requirement. For the RANS, one of the most important meshing requirements is the first cell height. Remember what I was showing here for the Y plus, and to capture the, I don't have it there, to capture that shape for the log layer for the Y plus, we need a very tiny elements here to capture the severe gradient, the severe velocity gradient that is near the wall, and then we can relax it with that expansion ratio till we reach the outer flow where Y plus is not that important, and we are done. It turns out that the most important thing in the boundary layer treatment in your mesh is the first layer height, the height between your surface and the first layer. Because think of it, this is considered by the solver as the no slip boundary condition. This is the element where the no slip boundary condition is satisfied on one side and you have velocity on another side. So that's your whole solution. If that first cell height was too large, this means that you are not in the region where Y plus must be equal to 1. You are capturing another thing where Y plus is equal to 5, but that's okay. But what's happening inside this cell? What should you do? And actually, back then, because numerical computation or computational power was not that strong, scholars and scientists used to have a large first cell height around Y plus equal to 5, and they used to model what's going inside, and even in some cases, they did not consider that boundary layer treatment at all, and they forced the solution using the log layer function because they know the shape of the function, and they forced the CFD code to satisfy that velocity near the wall, and that's it. You don't need even to do that. You just have this mesh, and we are taking care of everything in the code inherently without knowing. But nowadays, with very powerful computational power, it's not becoming the norm in the industry now. You can visualize or resolve your boundary layer on a very on your personal computer in a 2D simulation. So the previous discussion means that the first cell height is very important, and the first cell height actually will be instead of Y here, because we can replace Y here to compute the U plus for the first cell height. We can replace just Y, which is the first layer height, by H, so we can get Y plus to be equal to 1. But Y plus is defined in terms of U tau, and U tau is defined of the shear stress at the wall, and the shear stress at the wall, I actually don't know it. So what I just said now is the chicken or the egg dilemma. So what should I do? Because of that, you can have two ways. You can either assume first cell height, go and do your CFD simulation, and then plot your Y plus values. If they are large, around 5 or 10 or more, then go for a smaller one. But this could be a little bit tedious, and I don't recommend that. There is a very nice tool. It's called the Y or the Y plus wall distance estimation. It's on CFD Online. CFD Online is the largest forum for CFD on Earth. And by the way, it's a forum of real scholars and scientists. To have an account on that forum, you must answer around 5 or 6 questions. It took me 6 years to answer some of those questions. Yeah, it took me 6 years because they change those questions every time, and it took me 6 years to be able to answer the set of questions that I was given one day. So you could trust most of the time what's being mentioned there. And why is that? This simple calculator actually is not devised by one of them or someone came up with it. No, it's an estimation or a correction. It's an empirical or an estimation equation that has been developed by Schlichting himself, the German scientist. There is a very famous book called Boundary Layer by Schlichting. He came up with an empirical equation that gives you an estimate of the first cell height. Give me the free stream velocity and your density, your dynamic viscosity, the boundary layer length, which means the length of your body. Most of the time we said the characteristic length is equal to 1, so you will always have this equal to 1. And your desired y plus value, you need it to be less than unity, or the maximum thing to be just 1. And then you hit estimate wall distance, it will give you the Reynolds number and what is the estimated first cell height. I've been using this in most my CFD simulations and they work very fine, very good. Most of the time I take that estimated wall distance and just divide it by 2 or divided by 1/3 as a safety factor, and most of the time I get in my most simulations y plus to be in a range of 1. So this is a very decent way of estimating the first cell height. Okay, this is considered as one of the most or the most important thing that CFD or a beginner CFD person should do in trying to solve a CFD simulation. I used to have an advisor in my home country, and he used to ask those questions in the master thesis defense if someone is using CFD simulation. And if the student did not answer these questions, then he would say that this student could not get his master's because he doesn't have an idea about turbulence. So it was a harsh requirement, but it's a very important one. For the meshing, if you are trying to do an LES, your grid is the filter, but the DES simulation, now you are trying to come up with a mesh for RANS and LES, remember that? This is a very delicate task to do it, even if you are using the improved versions of the DES simulations that has those shielding functions and wall modeling RES. And because of that, there is this nice document by Spalart again. It's called Young Person's Guide to Detached Eddy Simulations Grid. And actually, after you read this document, it's still again hard to generate one grid for DES simulations to an extent that the simulations that I showed earlier with their nice grid, I don't have it here, the nice grid. I wanted to generate a grid for my DES simulation. I printed Spalart paper and I was actually kind of cloning the mesh sizes to be able to come up with a mesh similar to what he has done. Okay, so I'm not always trying to disappoint you, but it takes some time. The time step. The time step for the RAND simulation model, it must be very high or larger than the Kolmogorov time scale, because there is a Kolmogorov length scale and there is a Kolmogorov time scale as well, but I didn't mention it. I don't want to confuse you. It must be very large compared to the Kolmogorov time scale, but at the same time, it must be very small compared to your problem physics. Why is that? Because if, for example, what you should be capturing in your problem must be or could be this time history of the velocity. If one selected this time step, this means that you are missing the dynamics that's happening in this. You are not averaging, because you are actually averaging the average. This could be considered like as if it's a double average. So you are assuming that the velocity is constant, is one value from this step to this step, but this is not true. You have a severe dynamics that's happening here. So one must respect that. And at the same time, you want it to be very small enough to be able to average, because if it's very small enough compared to the Kolmogorov time scale, then this means that you are not averaging the solution. You are trying to do a DNS simulation. And believe it or not, I was not thinking that this is a very important thing while I was doing that simulation, but one days I encountered that. I took the time step to be very small compared to are actually not the Kolmogorov time scale, but around like 100 times or 50 times, something like that. And my solution did not converge and did divergent. And I kept asking my advisor. He told me, what's your time scale? And we kept digging, and he told me, you cannot have that time scale to be very small enough, because you are disobeying, or you are violating your assumption in the RANDS modeling, which is the average. Okay. And that brings us to the definition of the Kolmogorov time scale. It's defined as your Reynolds number to the power negative half, square root, or 1 over square root of your Reynolds number, again multiplied by t, the time constant or the time period of one single motion, or one single period of your problem. And that t could be expanded, considered as L over U, as we defined at the beginning of the slides. And again, I like to take delta t to be equal t over 50 to 200, and make sure that you are satisfying the CFL after this condition as well. And judging the solution, after we do all of that, I like to plot histograms for y plus. You can plot the y plus at each point, but this might be confusing. I like to plot the histogram, so it just gives me an estimate of what are the distribution of my y plus values. And as you can see here, your y plus values must override the log wall or the wall log layer assumption or not, when your y plus uh, uh, went beyond 1. And the negative 5 over 3 log law for the inertial cascade, if you remember, these are two results that are done by me. Again, on the left hand side is the unsteady RANDS and the DS simulation. These are a single point in my mesh that I used to track the velocity history throughout the whole simulation, and record it and calculate the power spectrum density for the velocity at this point, and then plot this result. In most of the time, you should get the slope of this inertial scales to be equal to negative 5 over 3. Again, regardless of what is the type of modeling technique you are using. Here the RANDS is getting the negative 5 over 3, but with much smaller scales. It's not visualizing a lot of the small scales as the frequency goes higher. But the DS here, because of the LES solver, it's visualizing a higher scales, and because of that, you find that transition from the inertial range to the large scales are kind of in a smooth way. But here it's as if it's a discontinuity, just like this and that. Again, because this is all of it is modeled, this is resolved. Okay, so this is one of the ways that you can judge your solution. And I think I'm done now for talking, and let's consider the hands-on session. I will be trying to be consistent in the hands-on session. Again, we will consider the unsteady or the steady cylinder mesh, and this will be the CFD or the problem setup. And thank you. Questions? Okay, if you go to the website now, we will use the and you will find this project. This is our geometry. I already imported it in ISIM CFD. Now, just as not to mess this project for future sessions, I will just save it as another name, but you don't have to do this. ISIM project underscore 1. The first step, if you recall last time, was just naming. I right click on create part, and then I click here and name it as an inlet, and then I click on the left click on the mouse, I click on the inlet, and then scroll the scroll button. You will get the inlet, and then upper, outlet, lower, and then wall. I like to name it wall. Okay, and we have here our different boundaries. If we were to generate an unstructured mesh, then we must make sure that our surface is seen by ISIM CFD. This blue surface is the imported surface from the SolidWorks, or you can export SolidWorks to another extension, IGS or STP or STL, whatever extension that ISIM accepts, and make sure that you have a surface. This step for the surface is very important if you were to generate an unstructured mesh. However, I'm not going to generate an unstructured mesh. I'm going to generate a structured one using the blocking technique. So I will go to that surface and name it as fluid. I like to keep this step for naming the surface and use it inside the blocking technique. But however, you can go away with this step if you become very expert, because the blocking technique only works with the boundaries that you will assign the block's edge to it. So now I go to blocking instead of mesh. I create a new block, and what's the type of the block? It's cylinder fluid, and it's a 2D planar block, because I'm going to be having a planar block to generate that mesh. And I will hit apply, and once I do that, you will see here those edges or these vertices are the block vertices that has been created. And now if we were to mesh that block, let's go to blocking and then pre-mesh parameters and select copy parameters. What's copy parameters is that ISIM CFD copies the parameters from parallel edges to each other, and select these edges. So now you have this edge parameters are copied to that edge, and it shows you the direction. Why is that? Because you can have an equation for the spacing. For example, if you would like your mesh elements to be smaller here and larger there, you can define the spacing, and you can define the equation and the expansion rate for that spacing. This is very useful in the boundary layer treatment or in any regions where you would like to have a very coarse, a very fine mesh. Which one? Copy parameters. So for example, I like at the beginning to select copy parameters. If you select copy parameters, I choose that one. Okay, do you have that arrow now? Okay, that's good. And then I select this to be a uniform, because I don't want to have any function now. I want to have a simple mesh, and I'll just select 50 nodes and then hit apply. And as you can see, when I hit 50 nodes, ISIM CFD gives you the size of the large elements. If I were to make this 100, you will see the sizes here changes automatically. Okay, so it's a kind of a very powerful software.
If I hit OK and then this toolbox disappears, how can I go back?
Which one? Oh yeah, you can go to pre-mesh and edge parameters.
Okay.
That's it. And then go to oh, I didn't select even the edge, so just click dismiss, go again to pre-mesh edge parameters, and that's it. Select the other edges now, go to uniform and 50, I hit apply, and then dismiss. Now I would like to see my mesh. I will click pre-mesh. It will say mesh is currently out of date. Would you like to recompute it? I will say yes, and that's the mesh that you get. This is your initial block. Doing a mesh using blocking technique, it's a topology problem that needs a little bit of some practice. I totally encourage you to start with one block and then think of ways of how can you split it and then come up with your mesh. For example, in this mesh or in this problem, I would like to have an O grid, not a C grid. You can generate an O grid by doing a very simple technique, is that if you have your large block, which is not obvious here, if you have your block, you can divide it, split it in a manner from here, and split it from there, and split it again from here, and split it again from there. And after doing all of that, you can then delete that edge. But however, if you do this manually, you will be facing a very big problem. Can anyone tell me what's going to be the problem that you will be facing? If you are, what's that? So, if you do so, you will find that you will be having a redundant block here. So that block, if you are trying to mesh and a circle, you will find that this vertex, once projected to that circle, it will look something like that. It will be a very squeezed element. In reality, if you do this by yourself, you will find that. You will get that type of mesh. That point here, and then you will get 2 points there, and you will get 2 points here, and you will get 2 points here, and that's it. Your mesh elements here could be of a good shape or a good skewness, but here this whole 90-degree will be very highly skewed elements. To overcome that, what we do is that we will merge these two sides. If you are going to merge these two sides or these two edges, then you will be having only one edge, and this is the mesh that we're going to create. So it takes time to kind of grasp what is the topology of your mesh and how can you create it. So one of the good tools in ANSYS that you can click here, and I would like to have an O grid. I will add a block inside my block, select that block, and again mouse the middle mouse click and hit apply and regenerate. Yes, see what's happened? He generated it for me automatically. Okay, if we would like to do this by ourselves, it would take all that steps that I mentioned earlier. Okay, so then O grid in ANSYS is a very powerful tool. And I will go again for pre-mesh. I will select this edge now because I need to have mesh elements normal, and I will select 50 again, hit apply, dismiss, compute again the pre-mesh because I want to see it, and that's a nice mesh. But I don't need this block here, so I will delete it. Yes. And now what I have been doing is that I just created the topology of my mesh. I did not tell ANSYS CFD yet that please associate this topology with the current geometry. So to do so, I need to go to association, associate edges, and select project vertices. And I will ask ANSYS CFD to associate all these edges, okay, with that one, and that's what we get. At the same time, I will ask it to associate that edge with this edge, that edge. Okay. Oh, now I missed one of the association steps. So I have to go back. So go back again. Now go for the association again. Select all of these. Now we are good. Now this one with that one. Okay. 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 And this is the type of the mesh that we can get. As I showed you guys last time, we have highly skewed elements here. To overcome this skewness, we can smooth the mesh by orthogonality. But I would like to show you another powerful step, a powerful feature of ISIM, is that you can go to split, and I would like to split edge. And what I'm gonna do is that I would like to split this edge here. As you can see, whenever I selected that I would like to split an edge here, it showed me a rectangle. Why is that? Because from a topological point of view, you cannot split that edge without splitting the others, because this is created from an O grid. So if I click this now and I click the middle OK, see, it created new four vertices for me. Okay, and I'll click yes. What's the good thing of doing that? Because now I have this luxury. I can move vertices if you wish. I can do this. See what's happening when I'm gonna do that. See, the mesh is kind of skewed following this thing. So it's a very powerful tool. It gives you a way of how you would like to guide your mesh elements to keep your orthogonality. Okay, I will go back in that step if ISIM CFD allows me. Yes. And another good tool about this is that you don't want your large expansion ratio to be determined by the near wall expansion ratio. Now, if we go to the mesh or the pre-mesh and select the edges, you will find here that now when I select this edge, it selects this one only, which with 7 nodes. And now I can have something as for example, exponential. Okay, and I would like to have for example 40 nodes in that region with the first spacing. What's gonna be the first spacing? Can someone let me know what's gonna be the first spacing? Exactly. So now we are trying to generate the first cell height here, okay, through the spacing here, and then the expansion ratio. The expansion ratio is the constant for the function that you used. Okay, so for example, spacing 2, I will take it to be 0.01. But this number, I just got it from my mind. To do it formally, we should go to the problem physics, find the Reynolds number, the density, the mu, and then go to CFD online, Y plus calculator. Here it is. This is the estimated wall distance for the case study. Take that value, go back again to ISIM CFD, and for example, click apply. And I would like to see that pre-mesh again. Yes. So now that is what I get. See here, it's very near. It's very packed, but there is not. Moreover, I get a steep descent here, or a steep jump, which is not good. And you can link those. If you link those edges, ISIM CFD will try to have a nice a transition between edges, but I don't, yeah, link spacing. So link that one to that one, most probably. Target is that one, something like that. Click apply. No target edge detected, thank you. This is the reference edge. Okay, this is the target edge. Come on, man. Yeah, apply. Okay, maybe there is something I forgot, but anyways, reference edge, target edge. Okay, it seems like ISIM is not allowing me to do that. That's okay. And if you are done with your mesh, you just go to block, you go to your pre-mesh, and then convert to unstructured mesh. After you convert to unstructured mesh, you go to the mesh block or the mesh tab, where now ISIM CFD deals with this mesh as if it is an unstructured mesh. Okay. Remember, it's not a bad thing to have an unstructured mesh. It means that only this mesh comes with a connectivity matrix, because Fluent works only with unstructured mesh. Okay. We would like to export this mesh. Obviously, this is a very bad mesh. I'm just trying to show you guys how, or to demonstrate how we can deal with the. We would like to output the mesh. Our solver is ANSYS Fluent. Let's go to the boundary condition. For edges, we have the inlet. I will create a velocity inlet. For the lower, I will create a symmetric one for the time being. For the outlet, I will create a pressure outlet. For the upper, I will create a symmetry. And for the wall, I think I must create a wall. And these are my boundary conditions, but I did not specify my fluid. So I will go here. Remember, I named my surface to be fluid. So this must be, and it selects it for you, so you know what type of, as a fluid. And accept. And then write mesh, save current project, yes. Okay, it wants to open, and it gives you this window. This is a 2D mesh, so we must select 2D. And would you like to do scaling? I would like to do scaling. Why is that? Because I know that when I imported this surface from SolidWorks, I imported it in millimeters. And this is a very important note, because you must know what is the unit that you are working with in ISIM, because it will totally set your first cell layer height. So for example, when I entered 0.01 for the first cell height, this was 0.01 millimeters, which is 1 times 10 to the power negative 5 meter that I got from the CFD online estimation calculator. Okay, if I were to work in meters, I should have entered there 1 times 10 to the power negative 5. Okay, so this is a very important step. Or keep it as it is and do a non-dimensionalization or scaling thing, but I don't recommend that. So I like to scale it. I will scale it by 0.01. Actually, I must include another one. And this is just a 2D, so I will scale it in 2D. And I will name it as Fluent and hit done. If everything in this window, the console window, if everything in the console window is blue, then you are good to go. If any line in this window is red, then you are not good to go. If you took that mesh, even if it's after it is exported, and you got your .mesh file, which is here, and you tried to import it in Fluent with only one single message that is read here, Fluent will not read it. Okay, and go figure. Now, I will open just the Fluent case, and next time I will continue in this simulation, which is the unsteady CFD turbulent simulator, which is this one. Which is this one, because I'm going over time. I will do this simulation, but next time I will not show the mesh. I wanted to show the mesh this time because I felt last time it was very quick and it was not a detailed or a recorded one. And next time it will not be very a long session. Please come up with question next time, because I will try to dedicate only 1 hour or at least for the lecture type session, and the next hour I will try to answer questions or do some CFD simulations, because when you utilize all of those 3 workshops in your Fluent simulation, and you imported your mesh, you have your coupled solver, simple, whatever, you have everything, and you just hit run, you just clicked run, and your simulation is running, and you are seeing your residuals, and there is nothing for you to do except to wait for about a week or a month or whatever. If you reach that step, then you're good to go to just take all of this case and that file and this Fluent setup to send it to the HPC. So it doesn't need any a CFD or fluid or physical information from you or anyone to be able to do that. It just requires a long time or a huge amount of patience to be able to deal with the Linux system, to deal with the Fluent software from the text user interface instead of the graphical user interface. What we are using the softwares and what we are used to in using softwares on Windows are called GUIs, the graphical user interface. But in reality, you can do everything in the TUIs, which are the text user interface. And any command that or any button that you click on in the graphical user interface, you can have a command that's equivalent to that task and write it in that black console for the Linux, and actually Fluent replies to you in the black command by this window, by this console. So that's why I highly stressed reading the console all of the time, while even you are using the graphical user interface, because I have seen some people, and actually when you master the text user interface, sometimes you will find that it's very useful. Why is that? Because, for example, if you have 10 cases and you would like to change the velocity in those 10 cases, as if you are trying to simulate the airfoil at a specific Reynolds number and you would like to change the Reynolds number, doing this through the graphical user interface is a pain and a hustle job. The number of clicks that you're going to do and the procedure and the steps for these and their order, you will miss one of those cases, I'm pretty sure. But however, if you know how to deal with the text user interface, you can write a code where just it reads the case file, it goes to the velocity, it changes the velocity, it saves the case file with another name, and that's it. And you can copy that code multiple times in one text file and give it to Fluent. Please proceed with that, and then Fluent will do it for you in just in a couple of minutes, in a seconds actually. It will be much faster than actually doing it through the graphical user interface, because actually I always suggest this, even if you're running a simulation, running a CFD simulation on the same machine, for example on a Windows, opening the graphical user interface, monitoring the residuals or the integral force by your eyes could be around 2 or 3 times slower than running the same simulation but just storing files or storing data to files. Why is that? It's something related to computing. Displaying information on a window on the screen is the most slowest process that computers can ever done or can ever do. So that's why I totally encourage dealing with Fluent in the text user interface. It will be much faster and it will help you a lot in doing a CFD simulation on HPC. And the last advice is to use Fluent on Linux, because I have done this homework by myself, running a CFD simulation from the text user interface on Windows and on Linux, the same case, the same everything, the same release, the same machine, everything is the same exactly, but doing it through the Windows took 2 times what you can do it on Linux, because the Windows operating system is not optimized for very fast sequential crushing number processes. It keeps checking all its peripherals and the mouse and the hardware and everything. This takes time in the background, and if you run a Fluent code and went to the task manager, you will find that Fluent actually is utilizing your processor up to 100%. So if you give Fluent 3 processors, the 3 processors that you give it to Fluent, they will be utilized up to 100%. Fluent is a very optimized C++ code that needs a little bit information